AI systems are beginning to supervise themselves while they work, not after the fact. Compiler feedback now reaches Claude, GPT-5.3 Codex, and Gemini during generation. Multimodal models can judge images by reading them back as text, and pruned Qwen-3 models can recover through their own rollouts. The broader shift is from static generation to closed-loop intelligence. Models generate, inspect, and adapt when feedback is most useful. That means fewer cascading code failures, stronger image alignment without a dedicated reward model, and cheaper recovery of lost reasoning after compression. Let's explore the first paper, Generative Compilation on the Fly Compiler Feedback as AI Generates Code. Researchers from ETH Zurich and the University of California, Berkeley, including Martin Vechev and Don Song, introduce generative compilation, a method that gives large language models compiler feedback while they are still producing code. Instead of waiting for a complete file, a lightweight transformation called a sealer closes each partial Rust program with syntax and typed placeholders, then reuses rustc to detect genuine dead ends. Diagnostics are mapped back to the original prefix, allowing black box APIs such as Anthropic's Claude Opus 4.8, OpenAI's GPT-5.3 Codex, and Google DeepMind's Gemini 3.5 Flash to revise earlier code without constrained decoding. The approach is formally developed for featherweight Rust, with completeness and selective soundness mechanized in Lean and extended to real Rust using control flow, placeholders, whole div, and whole val. Across 7 models on 20 cross-bench translation instances and 30 updated API projects, post-generation feedback reduced the average compiler error rate from 65.9% to 20.7%, while generative compilation lowered it further to 13.1% and achieved the best functional correctness result in 11 of 14 model task configurations. In a replay analysis, generative compilation detected errors at 33.3% of file generation on average, compared with 40.3% for function level checking and 100% for post-generation feedback, while its median diagnostic appeared only 3 lines after the eventual error source versus 89 lines for post-generation checking. The result is an on-the-fly compiler loop that reduces error cascades while preserving rich diagnostics and black box model compatibility. Let's explore the second paper. Read it back. Pre-trained MLLMs are zero-shot reward models for text-to-image generation. Researchers from the University of Hong Kong, Peking University, and ByteDance Seed introduced Spectra Reward, a training-free reward function that converts a frozen, pre-trained multimodal large language model into a text-to-image reinforcement learning evaluator. Instead of asking an MLLM to assign a noisy scalar score or decompose a prompt into verification questions, the method performs one image-conditioned, teacher-forced forward pass and averages the log likelihood of the original prompt tokens. Higher likelihood means the image can more reliably be read back as the requested description. Self-Spectra Reward applies the same principle inside a unified multimodal model, using Bagel's understanding branch to reward its own generation branch, with no external reward model or preference labels. Across 2 generators, 3 RL algorithms, 9 MLLM backbones, spanning 4B to 235B, and 5 out-of-distribution benchmarks, the method consistently improves prompt following. With Bagel at 512 resolution, Spectra Reward raises TIIF bench overall short prompt performance by 10 points and reaches 89.5 on Genevol with Self-Spectra Reward, while Self-Spectra Reward reaches 0.76 on WISE with Self-Chain of Thought evaluation. Notably, reward model scale is non-monotonic. Qwen-3V L23 5B A22B underperforms smaller models, while policy-aligned self-reward matches or surpasses much larger external evaluators. The strongest results suggest that tokenizer, vision encoder, and data distribution alignment can matter more than raw MLLM size for image generation RL. Let's explore the third paper, Short OPD Recovering Pruned LLMs with Short to Long on Policy Distillation. Short OPD from researchers at ByteDance and the Chinese Academy of Sciences addresses a failure mode in structured pruning. Compressed models can retain correct trajectories in their sampling distribution, while greedy freeform generation collapses into repetition. Using block influence pruning on Qwen-3 4B Instruct, the method keeps the pre-pruning model frozen as a teacher and applies on-policy distillation with dense token-level generalized Jensen-Shannon targets using the top 100 logits plus tail mass. Its novelty is a repetition-gated, short-to-long rollout controller. It detects terminal periodic suffixes, treats the surviving prefix as the effective length, and uses exponential moving averages to shrink or expand future budgets. On a 45,447 prompt corpus spanning GSM 8K, Math, NVIDIA, OpenCode Instruct, MBPP, Share GPT style instructions, and UltraChat 200K, 25% pruning reduced the 8-task generation average to 5.71, while one epoch of short OPD restored it to 48.46 compared with 30.52 for conventional teacher force KD. Evaluation included GPT-5 judging for open-ended tasks. Short OPD reached this quality in 8.5 hours versus 35.9 hours for a fixed 8192 token horizon, using 250M rollout tokens rather than 869M, while staying within 2 average score points of the longer schedule. The study argues that post-pruning recovery should target the compressed model's own states with dense teacher supervision and dynamically allocate compute as generation quality improves. That's a wrap on today's AI paper highlights. Thanks for watching.